After students learn both the washer and the shell method, they can get a little confused about which method to use. Let's look at a couple of volume problems where we focus on visualizing the cross-section for the different methods and then setting up the integrals. For this one, we're going to set up the integral or integrals needed to find the volume V of the solid generated by revolving the region in the first quadrant bounded by y equals 4x, a line, and y equals x cubed about the y-axis. The graphs have already been sketched. Let's go ahead and remind ourselves we're revolving about the y-axis, and I'm also going to label each of my graphs. Let's visualize taking the region and rotating it around the y-axis. For this example, I would say the washer and the shell method have about the same level of difficulty. So let's start by visualizing a sample shell. I went ahead and picked a sample x value on the interval from 0 to 2 to draw my shell height. Notice that the height of the shell is parallel to the axis of rotation. Keep that in mind, shell parallel. Now let's go ahead and draw the entire sample shell. Here is our sample shell. It looks like a hollowed out cylinder. Again, we can see the height of the shell is parallel to the axis of rotation. And so we can find the height by doing top minus bottom. So we have that h is equal to 4x minus x cubed. And then the radius is found by doing right minus left. So the right side down here is this generic x value, and the left side is the axis of rotation, which is at 0. So the radius here is just x. Now let's set up the integral using the shell method. So our volume V is going to be the integral from x equals 0 to x equals 2. So our region lies along x values from 0 to 2. Remember, we picked a generic x value in that interval. And then the formula for the shell method is 2 pi. And then the radius, well, the radius as a function of x was just x. And then times the height, which we said was 4x minus x cubed dx. So we can again, try to visualize all of the different shells. This was one sample shell that they're going to be extending from x equals 0, again, rotating around the y-axis, and then moving along the x-axis, getting closer to 2. So let's draw one more sample shell just to make sure we really understand and can visualize. So at this random x value here, I've went ahead and drawn a shell height and then drew my sample shell at that particular x value. So hopefully we can visualize a little bit more what the solid would look like using shells as cross sections. Now let's go ahead and do the exact same problem, but this time using the washer method. The washers need to be perpendicular to the axis of rotation. I'm going to go ahead and pick a generic y value here to draw a sample cross section. So here I'm going to start from the axis of rotation at this y value, and I'm going to go to the function that is furthest away to find my big R. So let's go ahead and start drawing our cross section here. So right at this y value, I've gone ahead and created a disk with a radius of big R. But I need to cut out that inner piece to create the washer. So that inner radius is going to be found by starting at the axis of rotation and then going to the closer function. So it's right at that same y value, but I'm using dashed lines to indicate it's a different radius. And so we're going to have that inner radius here, and I'm going to go ahead now and sketch that inner part to create the washer. All right, so here is my sample washer at this one y value. So we can see that they are all going to stack up vertically along the y-axis, extending from y equals 0 to y equals 8. And we're going to need my big radius as a function of y and my little radius as a function of y. So we're going to need a right minus left here. Our functions were given as functions of x, so we're going to need to solve to be a function of y. So our line is going to be x equals y divided by 4, And our cubic is going to become a cube root. So we're going to have x is equal to the cube root of y. Let's set up our washer method. We're going to have v is equal to the integral from y equals 0 to y equals 8. We said our cross sections are perpendicular to the y-axis, stacking vertically. And then we're going to need pi times the big radius squared, so the area of the bigger circle, minus pi times the little radius squared. So let's go ahead and set that up. We're going to have pi times the big radius, which is right minus left, the cube root of y minus 0, just the cube root of y squared, minus, we're going to carve out that little circle, pi times little r squared. So we're going to have pi, and the little radius, right minus left, is y over 4 minus 0 squared. So we'll just have y over 4 squared, and then dy. And for both the shell and the washer method, we can factor out the constant multiples. So we could have taken the 2 pi out of the integral. And here, since both terms have a pi in common, we can factor that out and then pull it out of the integral. So for the shell method, we have 2 pi, the integral from 0 to 2, of just x times the quantity 4x minus x cubed dx. So a really nice integral to evaluate if we had to finish it up. For the washer method, we have pi times the integral from 0 to 8 of y to the 2/3 and then minus y over 16 dy. So still not a terrible integrand to work with, but the washer method maybe is a little bit more work because we needed to rewrite the functions as functions of y instead of what we were given, functions of x. Here we want to set up the integral or integrals needed to find the volume V of the solid generated by revolving the region bounded by y equals 1 over x, so this decreasing function here, y equals 1 over x, and y equals the square root of x, that's the increasing function here, between x equals 1 and x equals 4, so this highlighted region, in part A, about the line y equals 2. So the axis of rotation here is a horizontal line, y equals 2. Let's think about taking this region here and rotating it up around this horizontal line. The method that I'm going to use is the washer method. And the reason is because if we use the shell method, we would need 2 separate integrals. Let's talk about why for a second. So shell parallel, our shell height, would be parallel to the axis of rotation. So if I think about parallel lines to the axis of rotation, it depends on the y value that I pick, what function the height is going to be touching. So if I pick a y value, let's say right here, then my shell height is going to be from the 4 to the square root function. And then if I pick a y value down here, then I'm going to have a right function of 4, but a left function that is the reciprocal function. And so there's those 2 separate integrals I would need to do from 0 to 1 and from 1 to 2. If I use the washer method, I don't need 2 separate integrals. If I start from the axis of rotation to find my big radius, and then from the axis of rotation to my closer function to find my smaller radius, little r, over the entire interval from 1 to 4, that big radius is always going to be the same, and then that small radius is always going to be the same. So over the entire region, the top function and the bottom function stay consistent. So let's set up using the washer method. The volume is going to be pi times the integral from x equals 1 to x equals 4. So our cross sections are going to be stacked vertically, perpendicular to the axis of rotation, from x equals 1 to x equals 4. And then our big radius is going to be top minus bottom, so that's 2 minus 1 over x. So 2 minus 1 over x quantity squared, minus my little radius squared, so 2 minus the square root of x as a quantity squared, dx. So let's take a second to try to visualize that cross section now. Here we have that cross section at this random x value here, And so we have that bigger disc with a radius of big R, and then we carve out the inside to create the washer, and that inside has a radius of little r. And we can see how they'd be stacking up perpendicular to the axis of rotation from x equals 1 to x equals 4. Now we have the exact same region, but we're rotating about the vertical line x equals 5. So for this one, if I take this region and rotate around x equals 5, I'm actually going to use the shell method instead of the washer method. And let's talk about why we're not going to use the washer method. If we use the washer method, we start from the axis of rotation to find our big radius by going to the furthest away function. Well, if I pick a value here, then if I try to go to the furthest away function, I'm going to hit the 1 over x function, the reciprocal function. And if I pick a y value up here, then I'm going to hit the square root function. So there'd be a different big radius depending on the y value. And then our small radius would be the same each time, but it's going to need two separate integrals. So instead of using the washer method, I'm going to go ahead and use the shell method, shell parallel. So if I pick a random x value here and I draw a shell height, then the shell height is top minus bottom, and over the entire region, we can see the top and bottom function don't switch. So this is going to be my shell height, and then my shell radius is going to be found by doing right minus left. So here's my shell height, top minus bottom, and then the shell radius, r, right minus left, is going to be 5 minus x. And then that shell height, again, is the square root of x, the top function, minus 1 over x, the bottom function. And we are doing this from x equals 1 to x equals 4. So let's go ahead and set up our shell method. We have the volume is equal to, let's put the constant multiple 2 pi in front, the integral from x equals 1 to x equals 4 of that radius, 5 minus x, times the height, radical x minus 1 over x dx. And just to get better at visualizing, here is a representative cross-section at that random x value. And now let's set up the integral or integrals needed to find the volume V of the solid generated by revolving the region bounded by x equals y squared and x equals 4 in part A about the line x equals 5. So x equals 5 is a vertical line, and then x equals y squared is this sideways parabola that I'm going to label, and then the line x equals 4 is this vertical line. Now, if we're rotating around this x equals 5, let's think about what method to use. Now, if we try shell parallel, then the shell height would be parallel to the axis of rotation, so it'd be going straight down here. But if I think about this height and top minus bottom, the top function is the bottom function in terms of y. So the top function is y squared and the bottom function is y squared. So we can't do that. We have to think about this as a function of x. So we would need to rewrite x equals y squared as y equals plus or minus the square root of x. So we would need to rewrite this as two different functions of x to get a top minus bottom. Not to say that we can't do that, so it's definitely possible, but I'm not going to do that, and instead I'm going to use the washer method just to avoid having to rewrite this as a function of x. So my washer method would look like starting from the axis of rotation to the function that is furthest away to get my big radius. And then my big radius would be right minus left as a function of y. And so we would have 5 minus y squared, perfect, because it's given as a function of y. And then my little radius that I'd have to carve out to create the washer from the axis of rotation to the closer function is little r, and that's always just this distance of 1. So right minus left, 5 minus 4 is 1. So it happens to be constant in this example. So to set up our washer method, we're going to have that the volume is equal to pi times the integral from, let's see, we need y values, and this is from y equals -2 to 2. So that's the y values where the region exists. So y equals -2 to y equals 2 of the big radius. So that's 5 minus y squared squared. Big R was right minus left. And then minus the little radius, that was just 1, right? 1 squared. And then dy. So this would give us the volume using washers. And just in case you were thinking, can I use symmetry? The answer is yes. So I could have set up the integral from, let's say, 0 to 2, especially if I had to evaluate this completely, not just set it up. We would double this integral. So 2 pi, the integral from y equals 0 to y equals 2. And then of the same integrand, quantity 5 minus y squared squared minus 1 dy. And now let's take that same region and rotate about the line y equals -2, this horizontal line below the region. For this one, I'm going to use the shell method, right? So shell parallel, my shell height would be parallel to the axis of rotation. And so if I pick a random y value here and I draw a horizontal line that's going to be parallel, that's going to define the height of my shell. And to find that height, I can do right minus left. So the right side is 4 and the left side is y squared. So my height is going to be 4 minus y squared. And then the radius of my shell is going to be this distance here, which we can find doing top minus bottom. So y minus -2 is y plus 2. So that's going to be the radius of my shell. Now let's draw that sample shell now. So here's my shell. It's still that hollowed out cylinder, but now it's lying on its side. And we can go ahead and set up our shell method. So our shell method, our volume, is going to be 2 pi. I'll leave that on the outside. The integral from, all right, so our limits of integration have to be y values. So this extends from -2 to 2. So we have y equals -2 to y equals 2. And then the radius times the height. So the radius, we said, was quantity y plus 2. And the height is the quantity 4 minus y squared dy. And so a couple of things. On this one, I actually cannot use symmetry. So here we're rotating around this line, y equals -2, below the region. And so my shells are going to start out traveling a shorter distance between -2 to 0. We can think about rotating them around, but they're going to travel a longer distance as I continue to move from 0 to 2. So I cannot use symmetry with the shell method here. And then just to explain why we did not use the washer method, for the same reason as the last one, if I were to have used the washer method, if I start from the axis of rotation and I attempt to go to the function that's furthest away to find the bigger radius, I'm going to hit the function x equals y squared, and then to the closer function is still x equals y squared. So I would have to rewrite this to be y equals plus or minus the square root of x. And so the top part is positive the square root of x and the bottom is negative the square root of x. It's still possible, just a little bit more work to solve to be a function of x. But that was the reason why I avoided doing that. And also so we could see another example with the shell method as a function of y to see these sideways shells.